Okay, welcome to this video for Chem 161, looking at some content for Chapter 6, where we'll be talking about intermolecular forces, as they relate to many of the properties of molecular compounds and materials. So we'll first try to distinguish between intermolecular forces and intramolecular forces. So to be very clear here, an intramolecular force is something like we've seen before already, and this is a bond inside a molecule. Okay, so these would be things like our covalent bonds that we've already spent some time on in the course. Now, an intermolecular, the ER means between molecules. Okay, so we'll see that these intermolecular forces, or often abbreviated IMF, is an attractive or repulsive force between molecules. All right, so we've got to be talking about two or more molecules that are not bonded to one another through covalent or ionic means, and we're going to address what type of attractive or repulsive forces exist between those separate molecules. Okay, so looking at that, what we now want to do is understand that there's different types of these intermolecular forces. Okay, so we'll start now with a list, and there are three main types. The first one is what we call London dispersive, dispersion forces, okay? London dispersion forces. These are very weak, okay? So these are weak forces. And we'll see that they occur between all molecules and atoms. So between all molecules and atoms. Okay, so we can expect to find this in almost every case of a mixture of atoms and molecules. All right, and what it is it's the attractive or repulsive forces that occur from a temporary dipole moment caused by a distortion of the kind of electron cloud or orbitals in molecules.
What's going on?
So what we're looking at there are things like shown in this animation, where this could be molecules of H2, so we could have three H2 molecules here. And temporarily, we'll see a distortion in the electron cloud, leading to a temporary shift in the electrons to one side of the molecule. So when we see a minus location develop, we can see that the electrons are going to be located over on that side momentarily, and we would therefore expect a minus to occur on that side, and as a consequence there would have to be a delta plus, and so this would result in a temporary dipole moment. Okay, so the electron clouds can distort with time, and when there is this distortion, we have now some shift in the electrons, pushing minus charges as a delta minus on one side and a resulting delta plus on the other side. And now we have a reason that these might attract other delta pluses that have been temporarily generated on neighboring molecules nearby. Okay, so that's a nice visual for that one. Okay, what we'll also know here is that the attraction will increase with a couple of features of the molecules in question. So, one, the physical size of the atom or molecule. Okay, so I'll put in parentheses here, contact area okay. And two, we'll see that this can also increase with polarizability. Of that electron cloud. Okay. A way to think about this might be the sloshiness, how easily shifted that electron cloud might be from one side of the molecule to another. Okay. So we call that polarizability. Electron clouds that are very large, very far from the nuclei would be easy to distort. So when we deal with very large atoms deep in the periodic table, very large orbitals would be used to make up those molecules and connect them together. The resulting electron cloud would be expected to be large. This would be sloshy or very polarizable. This would lend to stronger London dispersion attraction. Okay, so that was a big one. That one's, you can see, going to be very weak, we mentioned here, and it relies on a temporary result there. Okay, the next one we want to address is the next most strongest. And we're going to see here that we can have dipole forces. And these will arise when we have permanent. Okay, so these are kind of strong forces. And they result by attraction between permanent dipoles in a molecule. Okay, so we have to be able to list whether or not there's a permanent dipole, a net dipole moment in a molecule. Okay, so here we're going to look to some of the skills we learned in Chapter 5 for predicting molecular polarity. And therefore, if a molecule is polar, we know that there is a permanent dipole, and we can expect dipole-dipole forces. Okay, so just as a reminder there, this is caused by polar bonds. And asymmetry. In the molecule. Some lessons that we picked up in Chapter 5 there. Okay, and so what we'll see on this one are things like here. So if we look at the HCl molecule, we'd expect that chlorine, being the more electronegative, would have a delta minus, and it would shift the bond between that and the hydrogen, making it very polarized, shifting it towards that electronegative chlorine, and leading to a partial positive charge at the lesser electronegative hydrogen end. Okay, this pattern repeats across all HCl molecules, and as a consequence, we might expect some forces between these two, okay? So delta minus will interact with a delta plus in three-dimensional space, and likewise for the opposite, the delta plus from a hydrogen will interact with a delta minus to another molecule, okay? Okay, and the third one that we'd like to touch on is the strongest. And the third one is the hydrogen bond. And unfortunately, this name is not the best choice because we're using the word bond, but remember, we're talking about attractive forces. So we're not going to sort of show a hydrogen bond with a dash like we've done for covalent bonds. So let's be careful with this one. Again, we're looking at kind of attractive forces between molecules, and we're not going to use a solid dash to indicate a covalent bond, but there's some attractive force specific to a hydrogen atom on a molecule. Okay, so this is the strongest kind of dipole type result. Okay, so because we're dealing with hydrogen, relatively electronegative, weak in electronegativity, we can expect some dipole-dipole interactions here. And the hydrogen bond is one of the strongest intermolecular forces, okay? And our requirement for this is two things, okay? So we'll put number one. We need to have a hydrogen atom bonded to an electronegative atom. So what this is are atoms of types, and there's only three here that we'll list: F, O, and N. So if we find that there's a hydrogen bonded to one of these F, O, or N atoms in a molecule, we've set up the first condition for a hydrogen bond, okay? As a way to remember this, I tell myself that hydrogen bonds are fun, F-O-N, hydrogen bonds are fond. The second requirement we have, number two here, is that we need lone pair electrons on a small electronegative atom. Okay, small atom that is electronegative. Okay, and fortunately for our understanding, it's the exact same three atoms that we're looking for here, F, O, and N. All right, so to generalize this, what we're looking for here is molecules that have a functionality like this. There's some element X. We know what X must be. It must be F, O, or N, and it has to be bonded to a hydrogen. So here's a covalent bond right there, tethering the hydrogen to X, and the rest of the molecule is over here. Okay, and then here is the IMF, intermolecular force, that is the hydrogen bond. And it's going to result across to another molecule, so the rest of the molecule's over here, and there's a feature Y. That feature is Y is an atom of F, O, or N. Okay, so we could have, for example, Y as oxygen, we could have X as nitrogen, and we would expect a hydrogen bond to result for the hydrogen between X and Y on two different molecules. Okay, so there's their hydrogen bond, and this is the strongest dipole-dipole force that one can develop. Okay, so some takeaways here are that intermolecular forces are not as strong as covalent bonds. They're between molecules, so we're not going to draw explicit dashes, but think about attractive forces represented maybe by kind of dot, dot, dot type identifiers like this. The London dispersion forces are going to be found on all atoms and molecules. The dipole-dipole interactions, number 2. We need a permanent dipole, so we're going to look for these on polar molecules. We must have that permanent polarity in the molecule. And the hydrogen bond is sort of a building off that idea, except we have very specific situations. We need to have F, O, or N elements, one of which has to be bonded to a hydrogen, and a neighboring molecule has to have the same atoms, F, O, or N, and then we can think about an intermolecular force, okay? All right, so we'll leave it there. Those are the highlights, so please email me if you're still